So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have my colleague, Professor Navid Azizan, who is the Alfred and Jean Hayes Assistant Professor at MIT. And at MIT, he has dual appointments in the Department of Mechanical Engineering and the Institute for Data Systems and Society. And he's also a principal investigator in the Laboratory for Information and Decision Systems. So Navid's research, as many of you know, lies in machine learning, systems and control, and mathematical optimization with applications in network science. And the lab he runs at MIT focuses on various aspects of reliable intelligent systems with a specific emphasis on principled learning and optimization algorithms and applications in autonomy and socio-technical systems. So briefly about him, he got his PhD in computing and mathematical sciences from the California Institute of Technology. And before joining MIT, he spent some time at Stanford University as a postdoc. As you see from the bio, he has won many awards, both from industry and from the public. And the work has been really broad applications in a number of disciplines. Today, I think he's going to present an exciting topic, which is towards reliable and efficient AI-enabled autonomy. We are very excited to hear more about it. I will monitor the chat during the talk, so feel free to ask or raise your hand. But without further ado, Navid, thanks again for giving this talk. The stage is yours.
Thank you very much, Tiuele, for that kind introduction and for the invitation. It's certainly a pleasure to present here to this audience. So, yeah, I'm very excited to talk about this work that my group and I have been doing on broadly enabling AI for safety critical systems and in particular, reliable and efficient autonomy. So I think we all agree that this is an exciting time for autonomous systems as robots are being deployed beyond the carefully controlled environments of the factory floors into all kinds of new applications in settings such as our homes, the outdoors, our oceans, and our roads. And what sets these new applications apart is that here we are hoping to deploy robots and autonomous systems not in a carefully co-designed environment, but in the open world with features that are hard to model from first principles. And when I say autonomous systems, we're not just talking about robots. Of course, this also applies to our large-scale technological systems such as power grids, transportation networks, and all kinds of other societal networks that we have built as humans. And I would argue that to transition from automation in the factory to autonomy in the real world, of course, we need to grapple with these hard-to-model sort of features and nature of the world. And machine learning, of course, has demonstrably enjoyed a great deal of success in all kinds of applications to be able to capture these hard-to-model features of the work. So there are many examples. I'm sure you're all familiar with these. And what I want to say is, if you think about it, the kinds of applications that these models have been particularly successful for are when we want to get the most common use cases right, as in translation, or getting the right answer is not too critical. Examples of, I guess, recommender systems and so on. And sometimes they're tasked with making an expert faster, as in radiology or codecs and so on and so forth. So the question is machine learning ready for safety critical systems, for high stakes applications? And the answer is not quite yet. And there are many examples of how the outputs of neural networks can be brittle in unexpected ways. I mean, these are basically classical examples by now. You can fool the vision system if you put, for example, a few stickers on a stop sign into thinking that it's a speed limit sign. Of course, these models are extremely data hungry, and data is expensive for real systems. And there have been crashes and other unfortunate consequences. And I have a collection of funny failure examples of these LLMs. Sometimes they generate wrong outputs and very confidently so. So this is an example from GPT-5. You ask it to solve this simple equation. It goes on to, I guess, arrive at this wrong answer. The answer is 0.79 here. And when you ask it, how confident are you from 0 to 100%, it says I'm 100% confident that the solution is correct. So the point is, and well, of course, if you repeat this many times, you'll also get the correct answer at some point, and that's kind of what a lot of these reasoning models do. But the point is, we don't know when to trust the output of these models and when not to trust them. So the question is, what can we do about them? How do we enable AI for safety critical systems? And that's kind of the broadly the focus of my lab here at MIT. We develop theoretically grounded and practical methodologies to make AI reliable. And we work on a wide range of problems, ranging from opening the black box of these AI models, understanding their failure modes, their convergence behaviors, what happens when things go wrong, and basically try to fix those. We develop safety assurances for these models, which I'll talk about today, and then closed loop deployment and essentially learning for control and decision making. So back to this success of ML models, and I just want to mention that, of course, we see these impressive results with LLMs, with even things like self-driving, and that's largely driven by the massive amounts of data that has been collected and used for training these models. So machine learning models really require a lot of data, and available data is often limited. For example, considering all the different combinations of robot configurations, operating environments, and tasks, collecting data is very difficult. It takes a lot of effort for these different sort of combinations. And the question is, can we squeeze more from our data? Do we have any other source of information besides data so we can essentially get more information with limited data that we have? And one thing that my group and I have been focusing on a lot in the past few years is constraints. There are often different types of constraints. For example, the physical quantities often remain bounded. Systems are often stable. There are conservation laws of energy, momentum, mass, and there are, for example, symmetries in the problem that sometimes if you're predicting, for example, the state of the system, the change of coordinates should not affect that. So and these can help improve the generalization performance of the model. Satisfying constraints besides improving generalization is sometimes even a requirement. There are many examples of safety constraints. If you're dealing with for example, self-driving vehicles, there are all kinds of constraints like collision avoidance, keeping lane, speed limit, and so on. Of course, you don't want to break your robot if you're dealing with a physical system. There are all kinds of, again, safety constraints for not breaking your system and other sort of things in the environment. And there are all kinds of advisories that you may want your model to follow and so on. So the question is, how can ML models consider these constraints? And that brings me to, I guess, the outline of the talk, that this threefold approach that I'll present to reliable AI. Number one is constraining the behavior of the model during training. Then I'll talk about monitoring the behavior of the model during inference. And lastly, adapting the model continually during deployment. Okay, so let's start with constraint. How do we integrate constraints into neural networks? Let me do a quick review of what are the sort of existing approaches to handling constraints with neural networks. One of the most popular approaches that the control community, for example, worked on for several years, it's called verification. So this is neural network verification, or verification after learning. And there are many examples. There are a lot more papers on this topic that I could list here. But basically, the idea is, so there's some, let's say there's some data sets, xi, yi. You have this parametric function, which is a neural network, for example, f theta, that's trying to approximate the ground truth function. And then ostensibly, you do so by minimizing, let's say, the empirical risk on your training data. So after this training has already happened, neural network verification attempts to verify input-output properties of this network. And this is a very involved, computationally involved process. People have come up with all kinds of semi-definite programs and so on. I also worked on this problem a few years ago, and the part that I was always dissatisfied with is you work long and hard to verify whether a pre-trained network is safe or not. And in most practical scenarios, the network is unsafe. And then the question is, now what? And so there's another category of approaches that I call soft constrained learning. There are different variants of these. The gist of it is basically you penalize violations of the constraint as a regularization term. So for example, if you're trying to enforce this constraint, or you're trying to incentivize the satisfaction of this constraint, you add a regularization term that would penalize violations of this constraint on your training data. Okay. The problem with that, though, is first of all, there's no satisfaction guarantee for point-wise. Basically, there's no point-wise satisfaction guarantee. If you have a new sample and especially an out-of-distribution sample at test time, that's very different from your training data, you will lose satisfaction of the constraint. So the alternative to that is what we call hard constrained learning. And again, this is something that I'm very excited to talk about today. And that's what basically attempts to enforce constraint on all the inputs, no matter what the input is. So not just the training data, but on the entire input space. So let's get a bit more specific here. Let's say the input to the network is called X, and there are, again, parameters theta parameterizing this model. And there's an output Y. So why is this a difficult problem? What is, in a way, the desiderata? Well, the first property we want this to have is, of course, again, guaranteed satisfaction of input-output constraints for all inputs. We want to have still an efficient forward pass to be able to go from any X and any theta to a feasible output. That's for fast inference. And we still want to be able to train this data. So we need efficient so-called backward pass. We need to be able to compute the derivative of the output with respect to parameters efficiently to be able to train this network. And we want to make sure that this does not hurt expressivity. We don't want to lose all the nice properties of neural networks. We know that they have a lot of representation power, so that's a desired property that we don't want to lose. So just quickly reviewing the existing methods, this is a subset of what exists. There are a number of problems with these methods. Some of the existing methods work only for constraints that are a function of the output. So input independent constraints. There are other methods that try to incorporate input-dependent constraints, but they also have other issues. They often do not have satisfaction guarantees, or the satisfaction guarantees are asymptotic. They often rely on expensive solvers for their forward or backward pass. So they have this iterative sort of scheme that would have to be done both for the forward pass and the backward pass, which is not desirable. And oftentimes these are they can only satisfy equality constraints, which are easier than inequalities. And then the representation power of these are largely unknown. In contrast, what we show is this method called HardNet. It's again short for hard constrained neural net. It satisfies, it can enforce both equality and inequality constraints that are input dependent. You get a satisfaction guarantee for all your inputs, not just your training data. And the forward and backward pass are in closed form. So it's as efficient as it gets. And we also prove that these networks, these models essentially retain their expressive power and universal approximation properties. So let me show you how this works. Essentially, the way HardNet works is you have this unconstrained neural network, and then we append a differentiable enforcement layer to it. And this is in such a way that we can still backpropagate through this layer and train the original network the usual way with stochastic gradient descent or ADAM or your favorite optimizer. So this enforcement layer has a bit of a structure to it. So basically, there is a block that computes the constraints, and then the key here is a projection. I'll talk about what this projection is in a second. But the beautiful thing about this enforcement layer is that it satisfies all the desiderata that I listed earlier. So you get a guaranteed satisfaction of input-output constraints. You get an efficient forward and backward pass, and we prove that it does not hurt expressivity. So it does not over-constrain the network. It constrains it basically exactly to the extent needed. So this projection, let's think about what would be the first attempt if we try to project to the feasible set. Let's consider these affine constraints. So AX is a matrix, B of X is a vector. So these are input-dependent affine constraints. Even for these seemingly, I guess, simple set of constraints, if you try to write down what a Euclidean projection, I guess, would do is you try to find a Z that's closest to your to the output of your model, such that Z satisfies the constraints. And you want this to be true for every X. No matter what X you pick, you want this to be true. Okay. So the problem with this is, unfortunately, this Euclidean projection does not have a closed form solution in general, even for the affine case that I just described. And the key idea behind HardNet is essentially a closed form differentiable projection to this feasible set. And the way we do that is by essentially, it turns out if you replace the Euclidean norm in the objective with a Bregman divergence, and more specifically the squared Mahalanobis distance, you get a beautiful closed form solution, which looks like this. So it's basically a bunch of matrix multiplications and a nonlinearity value, and that basically happens on your unconstrained network. So this is actually like a linear, this is like a layer of a neural network. It's not linear. It's a layer of a neural network that you're appending essentially to the end after f theta. This is a very simple operation that you would do on your model, and this is the pseudo inverse of A. So this is beautiful. It's very nice. just to give you some intuition of how this looks, basically, if you look at this axis is the inputs, and these two, let's say this is a two-dimensional output space. So for any input, you have a particular set that's your the set of constraints. If I focus on an individual input, and let's say these two are my constraints, this is the feasible region. The unconstrained model gives you an output that's outside this region. And the optimization I originally described, which is, again, does not have a closed form solution, is this Euclidean projection. It turns out this other type of projection that I'm showing you here moves in parallel to this constraint, and more generally in parallel to the constraints that have been satisfied already. And it takes you to this feasible point. But again, the nice thing about it is that it has this very simple, beautiful closed form expression. And this has lots of applications. I'll show you a few. You can learn with piecewise constraints, even if they're essentially, yeah, they could have different sort of forms in different pieces of your input. And you can use this for optimizing learning optimizers, let's say, with guaranteed feasibility. You can also use it for optimizing safe control policies, for example, enforcing CBFs. You can enforce CLFs, and Eduardo has done some really nice work recently on universal formulas leveraging this work. And yeah, so I'll show you a few of these applications. Let's start with the piecewise constraints. And this is for illustration. So it's a single dimensional input and single dimensional output. This is my ground truth function. And then there are a bunch of training data points drawn from this, this function. And then we have constraints that are expressed in these by these red regions. So those are the violated areas. You see there are different constraints for different pieces. And you can also express them more compactly in this input-dependent form. What I want to emphasize is that if you use any of the methods from that table I showed you that are capable of handling input-dependent constraints, what happens is as you move outside your training regime, they start violating the constraints. And that's not surprising because you're at the mercy of your training data points to enforce the constraints. Whereas if you use HardNet, it satisfies the constraints perfectly, even if you're looking at a completely out of distribution sample. And you get, again, zero violation. And I want to highlight that even within the training data, because we are enforcing this constraint and we are essentially giving the model the right inductive bias, this gets a smaller error even on in-distribution data. And it's very efficient. The second example I want to highlight is learning optimizers. So this is something that comes up in all kinds of large-scale optimization problems in the power grids or any kind of system where you're solving a similar optimization problem over and over again with a different sort of input to your optimization X, with a different instance of your optimization problem. So people have used this idea of learning the optimizer to speed up the computation. So instead of solving this optimization over and over again, people have attempted to learn a neural network, to train a neural network essentially that learns how to map X to an optimal solution. So this has been very popular. And this is one particular example, I guess. The problem with these learned optimizers is that they do not guarantee feasibility. They attempt to give you something that's optimal, but there's no guarantee that what you get is even feasible. So there is an alternative. Basically, you can pose this as optimizing this as your loss function, and you essentially can take a neural network that by construction satisfies these constraints. And that's exactly what HardNet is useful for. You can compute feasible solutions with the smallest suboptimality gap and a fast inference. So I have many examples of these, but just want to show you that basically you get zero constraint violation, and you get a very nice objective. The objective value is actually the smallest compared to all the other methods, and it's very close to the optimal that you get from the optimizer at a fraction of the time compared to the optimizer. So this is very practical. The third example is for optimizing safe control policies or enforcing control barrier functions. So the problem is, let's say we have these dynamics, there's a nominal controller, and the goal is to compute a safe controller, and that would ensure that all the states remain within the safe set. Of course, CBFs have been popular for doing that. CBF-QP is essentially this quadratic program that tries to find the closest controller to the nominal controller that satisfies the CBF condition. The problem is if you have some other cost you want to minimize, so let's say you want to both remain safe and you want to optimize some other cost over a trajectory, this CBF-QP, at least in its native form, is not capable of doing that. But what you can do is you can define essentially your controller as the nominal plus some residual neural network. And that's a perfect fit for HardNet, because essentially you can enforce this CBF through the neural network by construction. Just to show you an example, this is an obstacle avoidance. There are two obstacles, and there's some cost functions that being optimized. I guess this is the starting point, and the final position is somewhere around here. You see that the CBF-QP stays safe, but is unable to optimize the cost. So we'll get stuck here at the boundary of that obstacle, whereas HardNet can stay safe and optimize the cost at the same time. And of course, the nominal controller, you'll see that it passes through the constraints, so it doesn't respect the constraints. So just to recap, I show you a differentiable architecture that enforces hard constraints. It has an efficient forward and backward pass. It also has expressivity guarantees. We show that this architecture, essentially with the appended projection layer, is a constrained universal approximator. And I want to emphasize that this is an alternative to neural network verification. So for me, this is full circle, because now I can get verified by design, essentially, networks without having to go through post-training verification. What if the constraints are not exactly known? Sometimes we may know the form of the constraints, but not the exact sort of parameters. And one example for that is this work on inherent Lyapunov stability. So let's say we're in a data-driven control problem. You have some completely unknown dynamics. So X is the state, U is the control input, and we're trying to learn this from some data in this form. So we have Xi's and Ui's and the derivative of the state. And the goal is to learn, again, a feedback controller that would stabilize the system, or without loss of generality, take X to the origin. The idea is quite simple. The idea is to enforce Lyapunov stability as a constraint and jointly learn that. So whenever we have a form for the constraint that's parameterized, but we don't know the exact parameters, we can use the exact same methodology I described with HardNet, and we can simultaneously learn the parameters in the constraint itself. So in this case, this is the stability condition. There are a bunch of unknowns in this. Of course, we don't know the Lyapunov function ahead of time, but you can learn that At the same time, I won't go through the details, but the form you can recognize is very similar to what I showed you in HardNet. So essentially, we're going to have a network consisting of three components. There's a neural nominal dynamics, there's a neural controller, and there's a neural Lyapunov function. And the way they're put together is that there's a projection that makes sure that this overall learned dynamics is stabilized by the controller that you have learned, and that Lyapunov is essentially a certificate for that. And you can show that the learned controller exponentially stabilizes the learned model, and the guarantees would transfer over to the true dynamics under the conditions that data is sampled with sufficient density and you train it properly to a small training error. There are many examples of this in the paper, but just to show you one on this bicycle path following, you'll see a convergence basically both for the learned model and also the true dynamics. So it works beautifully and it converges very well. Okay, so one other example that we've been recently able to show is for flow matching models. Unfortunately, I won't have time to go through the details of this one, but I just want to highlight that essentially you can enforce hard constraints while you're sampling from these flow matching or diffusion models via this trajectory optimization approach that we have. I'm happy to talk more about this offline if anyone is interested. It has lots of applications in robotic manipulation, maze navigation, PDE control, and even for vision problems. If you're doing a constrained image editing, we have demonstrated the versatility of this approach on a very diverse set of domains. So that's something quite exciting. And I'm very happy to talk about that offline if anyone is interested. So how do we enforce safety constraints on large-scale decision-making systems? As these systems get bigger, we run into some serious computational walls. Here's a simple example. Consider a composite action space, which is the product of n smaller action spaces. And we have a value function Q that I'm describing here. And to search for better policies, standard RL algorithms essentially try to do an argmax search at a given state X, but the computational complexity scales exponentially with the number of components n. So a practical way to handle this is to break the big problem down into smaller, more manageable pieces. And often these systems already have a multi-agent structure we can use. This leads us to this notion of safe multi-agent RL as a scalable way to learn safe policies. But this, of course, comes with its own critical challenges. First of all, existing methods mainly consider constraints in expectation. And for real-world applications, it's more reasonable to consider state-wise constraints. Second, multi-agent RL has inherent non-stationarity issues, and in the constraint setting, this becomes even more problematic since each agent's update not also impacts the reward, but also changes the feasible action space for other agents. And lastly, there are also challenges on handling feasibility and optimality. The constraint policy updates can be infeasible if you don't deal with them properly, and it's non-trivial to achieve optimality conditions. So we proposed this framework. It's a systematic framework for safe multi-agent RL that effectively addresses these challenges I mentioned earlier. And the key idea is to leverage a control theoretic method, I guess, namely the Hamilton-Jacobian reachability, for those of you who are familiar with it, for feasible region identification. And then, yeah, so you get very nice this constraint sequential updates that respects the respect essentially the constraint through this multi-agent setting. So yeah, so again, I'll be happy to talk about these other ones offline if anyone is interested. So, okay, just to recap this part, constraints can be efficiently integrated into ML models. They help with better generalization with limited data, and they also give us built-in safety and stability constraints. Now, we talked a lot about constraints. What if the constraints cannot be expressed mathematically, right? So if we have a problem for which the constraints cannot be expressed mathematically, and looks like my screen is somehow frozen now.
We can still see the slide.
Okay. Let me try to reshare. Okay, now the slides are advancing. Good. So sometimes the constraints cannot be expressed mathematically. The question is, can we at least tell when the models are making mistakes during inference? So these other two parts are going to be relatively short compared to the first part, but I think they're at least as important as that part. So as we discussed before, of course, the predictions of deep networks can be untrustworthy on inputs that are significantly different from their training data sets, and this can lead to accidents and undesirable outcomes. So if you have an out-of-distribution observation, that can lead to an incorrect model output, which can in turn lead to an unsafe outcome. The question is, can we equip pre-trained deep neural networks with the ability to quantify their uncertainty and detect out-of-distribution scenarios at runtime? And this is something that we have been working a lot on for the past few years. I'll show you a few examples of the methods we have developed. This is the first method we developed in this space. We call it SCOD. It's short for sketching curvature for out-of-distribution detection. So the idea is basically that we augment the model's output with an uncertainty signal, which could be used for better downstream decision making. And there's this saying that says all models are wrong, some are useful. I would say the models that know when they're wrong are more useful. So without going through the details of the math, let me show you a visual example of how this method works. On the left, we have images from a wing-mounted camera. This is an autonomous aircraft taxiing example. And there's a neural network that's predicting the distance of the aircraft from the center of the runway. And that's fed to some other downstream decision-making logic for decision-making. And on the right, I'm going to show you the uncertainty signal from our method, SCOD. And the higher this is, the more uncertain the model is. And whenever the model actually makes a mistake, I'll mark that with a cross. So you see that in the nominal morning, sort of clear morning conditions, there are no mistakes, and the uncertainty from SCOD is relatively stable. As we move into the afternoon, something interesting happens. The network starts to make mistakes. And in case you haven't guessed, that's because of this shadow coming to the picture. But our method is able to exactly capture that, and the uncertainty is higher than the baseline, so you can detect when this model is making a mistake. And as you move into the late afternoon, the network makes a lot more mistakes, and the shadow is more prominent. But again, the beautiful thing is that this uncertainty signal is much higher than the baseline, so it can actually tell you not to trust the model. And this uncertainty signal, we do a lot of quantitative experiments. We show that this correlates extremely well when the model is actually making mistakes. And I want to emphasize that this is model agnostic, so it can be applied to different tasks and different architectures. And it's extremely efficient. It's really a runtime monitor and works with any kind of data, not specific to vision. This was just an illustration. We have also extended these approaches to more generally representation models. The problem with representation models is the lack of ground truth labels in these abstract representation spaces. The idea is to use what we call neighborhood consistency. So you use neighboring points essentially in these different representations as anchors to align the representations, and we show that this idea is capable of doing uncertainty estimation in representation models. We have also extended this to large language models. This is a paper coming up in NeurIPS. Essentially, we show that if you calibrate the so-called process reward models, that you can make them accurately reflect the true success probabilities. And besides improving reliability, that's extremely useful for efficiency. It turns out you can do a much more efficient reasoning. You can save a lot of inference time compute while getting the same performance. So this has gotten quite some attention recently, and that's kind of what GPT 5.1 is also doing if you have used it. Okay, so what can we do after detecting issues at runtime? We talked about quantifying uncertainty of these models, and after we have done that, what can we do at runtime? Of course, we can use that to adapt the model. This is one example of a very exciting work that we've recently done. Of course, I'm biased, but I think it's a nice work. Essentially, the idea is to use the uncertainty signals that we have, for example, from Scott, to adapt our safety sort of constraints at runtime. So if you have a CBF, for example, you can do an adaptive to OOD measurements type of CBF, which essentially leverages the uncertainty signal that you have for adjusting the CBF dynamically. And this is an example of obstacle avoidance. So we use a cone-based CBF that avoids the heading angle to be pointed at the obstacle. So you see the algorithm, I guess, in action here. Just for the sake of comparison, if you do a CBF-QP, that's safe, but I guess it gets stuck here. Whereas ours is essentially able to optimize and remain again safe at the same time, leveraging the uncertainty signal I showed you earlier to adapt the CBF. So let's say we have deployed the model and we're able to detect these sort of issues and we can label these problematic data points. That's something that these uncertainty signals are useful for. We can select which data points to label and improve the model upon. But once we have collected this new data, there is another problem we have to deal with, which is what people call continual learning. So it used to be that in standard machine learning, it used to be that we learn the model we learn once, we train a model once, and we deploy it once. Now we're much more in this dynamic continual learning world where you continually learn from new data, and then you continually deploy this model. And so that's exactly the type of scenarios that are becoming more and more common in all kinds of applications. So the problem is basically you have data points arriving in a sequence, and you want to update your model with this new data without retraining on all the past, because that's expensive. You don't want to retrain your model on all the past data, and without causing what's known as catastrophic forgetting. This is a very well-known phenomenon in neural networks. If you train a model that you have already trained on some other data with a new data set that you have collected, it can completely forget essentially the past data. That's what's referred to as catastrophic forgetting. So can we update the model? Can we learn sequentially without catastrophic forgetting? It turns out there are ways to do that. We have this algorithm that we call ORFIT, short for orthogonal recursive fitting, which uses a very simple idea that is moving the parameters orthogonal to the directions that matter for the previous data. Again, I won't be able to go through the details, but if anyone is interested, I'm happy to talk about these offline. Speaking of, I guess, adapting the model, one of the central problems in real-time adaptive controllers for uncertain and nonlinear dynamical systems relies on a known parameterization of or known parameterizations or large amounts of data. This is in the context of adaptive control. Again, for those of you who are familiar with adaptive control, and I'm sure there are many in the audience, you can essentially, if you don't know these features a priori, you can leverage the meta-learning framework to learn the feature representations and the adaptation law essentially with a suitable geometry that's determined automatically. And we do this in a control-oriented fashion. So this is designed for directly optimizing the control performance rather than just fitting the data as in standard meta-learning. And we can show that this outperforms both standard control approaches and standard meta-learning approaches. And it uses some unifying theory of implicit regularization that we have developed with mirror descent that's of independent interest, I think, in machine learning. So lastly, I want to mention that if you're dealing with, again, large-scale socio-technical systems, these approaches are similarly, I guess, adapting the model is very useful in those contexts too. For example, in energy markets, if the operator is unaware of the cost functions of the suppliers, you can essentially do a dynamic pricing and you adjust the price over time and learn essentially the preferences of these agents over time. Okay, so just to conclude, I presented a threefold approach to make AI more reliable. I hope I convinced you that embedding constraints into the model can help both improve the performance and provide built-in safety and stability guarantees, especially on out-of-distribution test time scenarios. And when the constraints are difficult to express mathematically, we can design tools to monitor the behavior of these models and quantify their uncertainty. And lastly, by leveraging those uncertainty signals, we can adapt the models during deployment in a manner that is both data efficient and compute efficient. And this can be achieved through as I described, control-oriented meta-learning and continual learning approaches. So with that, I'll stop here. Thank you.
Thanks so much, Navid, for the great talk. A lot of cool stuff. Let's open the stage maybe for questions. You can either type in the chat and I will repeat the question, or you can just unmute, raise your hand and ask directly. So we have Murtavic. Yeah, go ahead.
Thanks, Navid, for this great presentation. So in the first part, when you showed the projection that you used, it was parameterized by matrix Q, but then the answer to the projection, the closed form, didn't seem to depend on it, unless I missed it. If you could clarify that.
Yeah, thank you, Murtavic. So basically, yeah, let me pull up this. Yeah, so Q has this special form in this case.
Oh, okay.
To get the closed form, yes, you have to pick that as A transpose A.
Okay.
Great question.
So to just quickly follow up on that. So in this basically framework that you presented, so if we take out this nice projection that you present with a closed form solution and use the Euclidean projection and put basically some iterative method to solve for that. So do we lose some other properties in your desidera that you mentioned?
Great question. Yeah, that's a great question. So the biggest problem again with this is if you attempt to do the Euclidean, of course you need some solve. You need to rely on some solver or some iterative method, which means that for every input x. So remember, as I'm training this model, my parameters theta are also changing. So for every input x and every parameter theta, I have to compute an output over and over again. So it quickly becomes very difficult. So again, the forward pass becomes very inefficient. And so that's one of the key, I guess, properties that you lose. If you manage to solve this exactly, we actually prove that even this Euclidean one preserves universal approximation. That's something that it's a new result. It's easy to show, but no one else, to the best of my knowledge, had shown that. So if you put the computational aspect of it aside, which is a big part of it, then we can show that yes, this satisfies the constraints and preserves the expressive power of the model.
Great, thanks. Yeah.
Thanks, Murtavic. And the next is Eduardo with a question.
Yes, hi. Great talk. I loved it.
Thank you so much.
And as you know, we've been using some of that stuff, the hardnet stuff. So, just a couple of little questions. First of all, obviously the method only works. I'm going back to the first part we was just asked about the Magellan-Nobis, whatever you pronounce it, method. So that's geared to affine constraints, clearly. Is there any hope to do something for, piecewise quadratic or whatever, some more general?
Yeah, excellent question, Eduardo. Thank you. So first of all, yeah, so these constraints are, let me go back to the form we have here. Yeah, so these constraints are affine in the output and still, of course, arbitrary functions of the input. And as I showed you, we can have piecewise constraints in the input. So A of x and B of x can have arbitrary dependence on the input. But yes, this is affine in the output of the model Y. We have recently been able to do this for also quadratic constraints, and that also has interesting applications for learning chaotic PDEs. So there is hope in extending this to other types of constraints, and I'm very much actively looking for different types of constraints. And
so just to clarify, you get some sort of closed formula, universal formula in some sense.
That's right. Yeah, that's right. We can get a closed form projection for quadratic constraints also. Again, arbitrary dependence on the input, quadratic dependence on the output of the model.
Cool. All right. I'll be contacting you to ask if.
Absolutely.
So, I mean, of course, in general, if we go back to, convex constraints in general, right, the people for 50, 60, 70 years have been looking at things like iterative projections. You take one constraint at a time, and then you can do contraction of that in many ways. So you have actually tested, if you would do that, how this works compared to that. And
Yes.
that's just convexity, right? You don't need hyperplanes in that case. In Y.
Right. Yeah. So for the convex case, we do have this, I guess, counterpart we call hardnet CVX. Of course, we have to pay some more computation there because
Sure.
the solver would be more expensive. So that's kind of the trade-off. Yes, we can enforce convex constraints, but that would be at the expense of, again, more computation for both forward pass and the backward pass.
Right. Well, what I meant is your case of this polytope is an example of a convex set. I was just wondering whether you compare even in that context.
Yes, we have. Yes.
Whatever.
Okay, very good. Yes, we actually have. Yes, we have that in the paper in the appendix. Yes.
Okay. All right. Good. Cool. And just if I can, just one last question. So I think if you go forward to, you had the neural controller and you enforce the Lyapunov, and you had the 3 neural networks.
That's right.
Right. If you could get to that slide, just a quick question about this. Yeah. So if I was doing this, I probably would have 2 neural networks. And for the neural controller, I would use automatic differentiation, as you're probably doing anyway, so you've got the gradient in there. You use automatic differentiation and then use a universal formula for the U star. And that way, the universal formulas would bound, even if you put boundedness on the inputs and things of that sort, right? So wouldn't that be slightly faster in terms of training, maybe? Of course, it takes a little freedom away, but I'm just wondering if you tried that.
Yeah, that's a great question. We haven't tried that yet. This is, I should say, the sequence is the way, I guess, we came up with hardnet. This predates hardnet. We first did this work first, and then we did hardnet. And so your recent work on this universal formula is very interesting.
Well, I didn't mean that. I didn't mean the recent work on CBFs and CLFs. I'm just saying, even if you forget about the constraints, right? You're generating a neural controller there, which is an arbitrary function at this point, right?
Right.
And now you can, this work going back 30 years or whatever, where there's universal formulas for stabilization part, right? But you could put constraints on the constraints on the input values, for example. So the universal formulas for CLFs with bounded inputs, for example, and then bounded. You want the feedback to be bounded or whatever in some convex set. The problem is still open, by the way. There are only partial results from 30 years ago. But anyway, but then you have the projection part. So, that's okay. But I'm just saying, maybe that would be worth trying to just try for fun. What happens if instead of having a 3rd neural network, you only train 2 neural networks, but you use the universal formula?
That makes sense. Yeah. That would be an interesting. Yeah, I think I agree. That would be an interesting
side project. It could be interesting.
Yep.
All right. Thank you so much. Great talk.
Thank you so much. Thank you. Appreciate it.
Thank you, Eduardo, for the great questions. There is another question in the chat from Mikael. Is the neural net optimizing in the unconstrained domain? In other words, it can violate constraints before they are addressed by the projection step. And if yes, can multiple inputs collapse into a single projected output?
Yeah, so the first question was basically, can the original neural network, I guess, violate the constraints? Absolutely, yes. So the unconstrained network can violate the constraints, and indeed it does in practice. So that's the whole basically role of this projection to bring back feasibility. I missed the second question. I think you're muted, Julius.
Oops. Yes, and it says, and if yes, can multiple inputs collapse into a single projected output?
And multiple, yes. So basically, I guess going back to this picture, that might make things more clear. Yep. So essentially, yes. If you have, for example, this point, the feasible projection would be the green I show you here. If you extend along this this green line up to here or anywhere, I guess, let's say here, of course, the feasible projection is the same point. But the key results, which I didn't have time to show during the talk, is that this projection gives you constrained universal approximation. So you do not lose the expressive power of the model, and you can represent any function that satisfies the constraints with this architecture.
Mm-hmm.
Great question. Thank you.
Okay. Yeah, Mikhail, if you have a follow-up, just write. But is there any other question for Navid from both the?
Okay.
Oh, yeah,
Can I
Mardavich.
ask one more question?
Yes, sure.
Okay, sorry. Okay, so Navid, so I understand this is a much nicer method, but just for comparison, I'm going to say something a little bit more trivial, not more trivial, a little trivial. But so let's say if you took one of the regularized methods that bring the constraints into the cost and they don't come with guaranteed satisfaction of the constraint, and then you did a final projection to guarantee the satisfaction. One-time final projection. So how would you compare that?
Excellent question. Excellent question. That's actually one of the baselines we compare against in the paper. You're saying, does training with the projection matter, or can I just train without the projection and insert it at test time? Yes. It turns out training with projection improves generalization performance. So there is a difference. We do have that as a baseline in the experiments. That's a great question.
I'll look it up. Thank you. Thank you.
Thank you for the question.
I was actually I was looking a little bit into this distance, and it's interesting. It was introduced 100 years ago to classify skulls. Very interesting.
Yes.
So you're doing some interesting archaeology.
Yeah.
It's hard to pronounce.
Yes. I just said the M distance.
The M distance.
Yes.
Nice. Any final question for Navid? All right. Doesn't look so. Thanks so much, everyone. Thanks so much, Navid. It was a great talk.
Awesome. Yeah. Thank you so much.
I'll reach out with the recording.
Thank you. Thank you.
Thank you.
Bye-bye.
Bye-bye.